Welcome to our video lecture of Precalculus 1.7, Transformations of Functions. The first transformation that we'll analyze is the vertical shift. And here we have a function f and a positive number k. So what we're going to say is that if you take the function f of x and you add k, you've shifted up your function f of x by k units. So you've added k to the y coordinates of the points on the original graph of f. And then if you subtract k, you've shifted your graph down by k units, and you've subtracted the value of k from all of the y coordinates of the original points of the graph f. So to illustrate a vertical shift and how it affects the y coordinate, so it affects the y coordinate of our parent function. Let's take a look at two shifts here, two vertical shifts. So our original function, our parent function is here, the red one. That's the absolute value of x. Then the green one is we're shifted down by 1, and the blue one is we're shifted up by 2. So let's take a look at this point here, 0, 0. So if it's 0, 0 here, it's going to be shifted up by 2. It'll be 0, 2 here. If I shift it down by 1, it'll be 0, negative 1 here. So let's take a look at one more point. So how about the point 1, 1? Okay, so if our point is 1, 1 on the parent graph, if I shift the y coordinate up by 2, I'll be here, so it'll be 1, 3. Okay, so this is 3 on my graph here. All right, and then one more point. If I take a look at my green graph, and I shift the point 1, 1 down by 1, I'm going to get the new point, the translated point 1, 0, because the y coordinate subtract 1 is now 0. Okay, so that's a vertical shift, and the vertical shift is applied to the y coordinate of the parent function. Okay, so now we're going to talk about the horizontal shift. Now the horizontal shift is a little bit more difficult to interpret because it's the opposite of what you would originally think. So for a horizontal shift, so this is a shift in the x direction. Okay, once again, your shift number is a positive number. So if you've got x plus h instead of x in your original function, that's going to shift your graph to the left by h units. So it's the opposite sign of this sign here. So if you add h to your x, you're shifting left. Now if you subtract h from your function, you're shifting right. So let's take a look and see how that plays out on a graph. So let's try to interpret why the horizontal shift occurs in the opposite direction. So we're shifting the parent function. So in this graph, the parent function is the absolute value of x. All right, and that's your red graph here. And then the blue graph is your translated function. And that's a plus sign there that's causing this graph. Now let's see if we can reason out whether that graph is really the true graph of the absolute value. So it would be the function of x is equal to the absolute value of x plus 2. So just to plot a couple points. If x is 0, then we've got the absolute value of 0 plus 2. So that's 2. Okay, so that's this point. Let's say x is negative 2. If x is negative 2, we've got negative 2 plus 2. That's the absolute value of 0, so that's 0. So that'd be this point. Let's do one more. Let's say x is negative 4. So then we've got the absolute value of negative 4 plus 2. That's the absolute value of negative 2, so that's 2. So that would be this point here. So what we've shown here is that your graph is this here. Okay, so what you can see, if you even keep plotting a few more points, that contrary to what we would have thought, our graph is moved in the left direction by 2 units. Okay, now let's look at how we would do a point-by-point translation. So if let's start with the point 0, 0 on the parent graph. Okay, so if we start with the point 0, 0, all right, and this is on the absolute value of x graph, what would that point be on the absolute value of x plus 2 graph? Okay, so remember we said the y value is not affected by a horizontal translation. Okay, but the x value is going to be moved. Okay, so the way that we can figure out a point-by-point translation, we say the old x value is equal to what happens to the input. X plus 2 is what happens to the input according to what you have inside here. So if I set that 0 equal to what's inside here, I can find a one-to-one correspondence between this point and the new point on the translated graph. All right, so I know I can subtract 2 from both sides. So that says x is equal to negative 2. All right, so those 2 points have the one-to-one correspondence. That one goes to this point over here. It's new version is negative 2, 0. Let's do one more. Okay, so let's take, for instance, this point here, the point 2, 2 on the parent graph. All right, so if I want to find out the corresponding point, where this point landed when I transformed it, remember the y value is not going to change, so but we need to figure out this x value here. So we take our x value and we set it equal to the transformation inside the absolute value bars, and we solve for that new x value. So that means x is going to be equal to 0. So that point 2, 2 moved over, and it is now 0, 2. Okay, so now you can see that this right here is your horizontal translation. Each of the points on your parent graph moved to the left by 2, and you could do that same kind of one-to-one transformation on each one of these points to figure out where each one of them moved. Okay, so let's try the transformation of the square root of x function. So let's plot 3 points on the square root of x function. So we'll make a t-chart. Okay, so remember underneath, we can't have a negative x value here. All right, so we're going to start out with 0 being our first x value. So that means the square root is 0, so that's equal to 0. So that's 1 point. Let's try 4. So the square root of 4, that would be 2. Let's see, what else could we do? Let's try 9. So 9, square root of 9 would be 3. Okay, so here's 3 points, 0, 0, 4, 2, and 9, 3. Okay, so let's plot those. So I've got 0, 0, 4, 2, and 9, 3. All right, so that's my square root of x function. Now, part 2 says, use your graph in 1 to graph square root of x down by 1. So this is a vertical translation down by 1. Okay, so if I take the points that I came up with for the parent function, I can look at those coordinate pairs. Let's do this one in green, and come up with the translated coordinate pairs of those 3 points. Okay, so the x value isn't changed when you were doing a vertical translation, so that's going to stay the same. But the y coordinate, according to our transformation, has to go down by 1. So I've got 0 minus 1, so that's minus 1. I've got 2 minus 1, so that's 1. And I've got 3 minus 1, so that's 2. So my new points are going to be here, here, and here. Okay, so I've done that. So now let's go ahead and do the third one, which is a horizontal shift. So we went into it in great detail on the last slide that if you have a negative in here, you're going to the right. So our translation is to the right one. So the net effect is the x-coordinate on the new point is going to shift to the right by 1. So if I write my new ordered pairs, when you're doing a horizontal shift, the y-coordinate doesn't change. And in this case, the x-coordinate is going to increase by 1. So this becomes 1, this 5, and this 10. So if I put those new points on there, I'm going to get 1, 0, 5, 2, 10, 3, and my whole graph has shifted to the right by 1 unit. All right, so the last one then says we've got a double translation. So we're shifting to the left by 3. That's left 3 and down 2. Okay, so that means both our x and our y coordinates are going to be shifted. So let's get rid of this. Let's pick a new color. So we'll do it in purple. Right? So we got to figure out our shifted points here. 2 things are going to happen. Okay, so the x-coordinate is going to be affected by the horizontal translation. So the horizontal translation is left 3. So I'm going to subtract 3 from each of the x-coordinates. So 0 minus 3, 4 minus 3, and 9 minus 3. And then I'm going to subtract 2 from the y-coordinates. 0 minus 2, 2 minus 2, and 3 minus 2. And I'm going to plot those points. So we've got negative 3, negative 2, 1, 0, and 6, 1. All right, so they still retain the same shape, but the purple one has been shifted to the left by 3 and down by 2. So that is how we can do a point-by-point translation and reconstruct the translated graph. Okay, so now we'll talk about reflections. So this first point here says to graph the function y is equal to the negative of the function f of x. So we're multiplying the parent function by a negative sign. we're going to reflect the graph of the parent function across the x-axis by multiplying the y-coordinates by -1. Okay, so a negative in front affects the y-coordinate. All right, so f of x is y. So a negative in front affects the y-coordinate, changes the sign of the y-coordinate. It doesn't change the x-coordinate. All right, but if you have your negative applied to the input, the x value, it reflects the graph across the y-axis by multiplying the x-coordinate by -1. Okay, so let's try that. So we're going to use these 3 examples to take a look at how the reflections play out in a point-by-point transformation of the parent function square root of x. So first we're going to plot, let's call it f of x. We're going to plot f of x is equal to square root of x, the parent function. And I'm going to use 3 points. So 0, 0, and then if x is 9, square root of 9 would be 3. That's another point. And x is, let's say, 4. Square root of 4 would be 2. Okay, so we've got 0, 0, 4, 2, and 9, 3. Okay, so that's our parent function. Okay, so as we said in the prior slide, applying a negative to the input value, so it's under the square root as opposed to in front of the square root, causes a reflection about the y-axis. So this graph here, we expect it to reflect across the y-axis and look like this graph here. So the way that we do that, and I'm going to transform each one of these points by applying a negative to the x value. Okay, so when you've got that negative underneath here, we apply it to the x value of the original coordinate pair. Okay, so the y value, let's do it in blue, the y value is not going to change. So the y value is going to stay the same as the original point. All right, but the x value is going to be negated. All right, so let's do that. So our blue graph is going to be 0, 0, negative 9, 3, negative 4, 2. And that, as you can see, is the reflected graph across the y-axis. Okay, on example number 2, we've got 2 things going on. We've got a negative in front of the x, and we've got an add 3. So 2 things are going on. So add 3, that means we're going to translate in the opposite direction by 3, because it's applied to the input value. This is a horizontal translation in the opposite direction. And the negative in front here is going to cause a reflection over the y-axis. You see, these are both things that happen to the x value only. Okay, stuff on the inside affects the x value of the original coordinate pair. So we're going to figure out the new coordinate pair, and the y values are not going to change. We're going to figure out the x value. Okay, so the way that we do that is we take the underneath part, 3 minus x, and we set it equal to the original coordinate, the original x coordinate. So for the first one, 3 minus x is equal to 0. So that means negative x is equal to negative 3, or x is equal to 3. So does that make sense? Let's think about it. So if we're doing 2 things, we're going left 3, and then we're reflecting across the y. If I've got this point here, and I go left 3, and then I reflect this point across the y, it would bring it over to here. So that point would be 3, 0, which we got. All right, so let's try the next one. So that means 9 has got to equal 3 minus x, so that's negative x is equal to 9 minus 3. X would be negative 6. So that point would be, let's put the first one on, 3, 0. Second point, negative 6, 3. And then the last one, 4, the x-coordinate 4, is going to equal to the underneath 3 minus x. Minus x is equal to 4 minus 3, or x is equal to negative 1. So 4, 2 becomes negative 1, 2. Okay, so this is our graph. And that graph has been translated to the left by 3 and then reflected over the y-axis. So as you can see, it's pointed in the opposite direction of our parent function, which is what you would expect when you reflect over the y-axis. Okay, so the last one, let's rearrange the order here. So we were applying a negative to the output this time, so that's negative is going to cause a reflection about the x-axis this time, and then we're going to add 3. Okay, so a negative in front reflects it about the x-axis, and a plus 3 on the outside means we're going up by 3. So 2 things are going to happen. We're going up by 3, so for instance, let's predict, let's say this point here, if we go up by 3 and reflect across the x-axis, we expect it to wind up down here. Now let's do our point-by-point transformation here. So both of the things are only affecting the y value on this problem because there's nothing happening to the x underneath the radical. Okay, so that means our x's are not going to change for this transformation. Okay, so for the y value, we're going to increase by 3 So that would be 0 plus 3, so that's 3. And then we're going to negate that. So that's multiplied by -1. So we're going to get -3 here. So the first point, 0, 0, now becomes 0, -3. See? And we're going to do the same thing for the second point. So the y value is 3. So we're going to increase it by 3 and then apply a negative. So if I increase it by 3, I'll get 6. And then if I apply a negative, I'll get -6. So that point becomes 9, -6. All right, one more. So if I have a y value of 2, and I increase it by 3, I get 5. And if I negate it, I get -5. So I've got the point 4, -5. Right? So now if I sketch it in, so you can see that things only happen to the y-coordinate in this particular transformation. So this graph was originally going to be raised up by 3 and then reflected over the x-axis. It brings it down here, reflected across the x-axis, so it's pointing in the downward direction now. Okay, so the next type of transformation we're going to talk about is vertical scaling. So that's scaling in the y direction. So if you have a graph that looks like this, y is equal a times the parent function, f of x, you're multiplying all of the y-coordinates of your parent function by a factor of a, which is going to cause a scaling of your graph in the y direction. So if your scale factor is larger than 1, it's going to cause your y values to get bigger. So it's going to cause your graph to, your points to be pulled upward. And if you have a scale factor between 0 and 1, it's going to cause this point to move downward. Okay, so you're either going to have a stretch, sometimes called an expansion or a dilation, or you're going to have a shrinking, sometimes called a compression or a contraction. So let's see how that would work on a point-by-point basis. So if we take our parent function, so the red one is your parent function, this would be x squared. And I look at this point 1, 1, and let's say maybe we look at another point here, 2, 4. So we've got 1, 1 and 2, 4. Okay, so a vertical scaling is done to the y-coordinate of your parent function. So I got to take of course, my x-coordinate is going to remain the same. So let's do the blue one first. So let's make this blue here. So the x-coordinate is going to stay the same. So the blue one, this blue function right here, has got an a value of 2 in front. Okay, so that means all of your y values are going to be multiplied by a factor of 2. So if I have 1, that's 2 times 1 is 2. If I have a y-coordinate of 4, that would be 2 times 4 is 8. So 1, 1 becomes 1, 2. So it becomes this point here. And 2, 4 becomes 2, 8. So it becomes this point here. So you've stretched it by a factor of 2. Okay? And you wouldn't expect that the length of this line to be the same because it's not adding 2, it's multiplying by 2. Okay, so this green graph here has a scale factor of 1/2, so that corresponds to this case here where the a value is between 0 and 1. So let's figure out how these 2 points move. So the x-coordinate stays the same, but the y-coordinate is cut in half. All right, so I'm multiplying 1 by 1/2, now I'm multiplying 4 by 1/2. So 1/2 of 4 is 2. So 1, 1 becomes 1, 1/2, so that would be this point here. And 2, 4 becomes, so this is 2, 4. 2, 4 becomes 2, 2, so it'd go down to this point here. Okay, so we've moved that much here, and we've moved that much here. So we've basically shrunk the graph, and some of the terminology that you see for this is compression, like in other words, like squashing it down, or contraction, making it shorter, or shrinking. Those all words that imply that you've pushed this red graph downward, and it's become this green graph. And so any words for having a number in front, an a value greater than 1 is, let's go back here, we say expansion, dilation, or stretching. Those words mean you're raising that point up. Okay? So when we have horizontal scaling, we're talking about affecting your x values in your coordinate pair of your parent function. All right, and the y value would not change. So your scale factor is beside the x in your function. So if you had a square root function, for example, your scale factor would be underneath the radical, or an absolute value, your scale factor is inside, something like that, or a squared function, you'd have it inside before you squared it. So we're applying the scale factor to the x value, the input value, and that affects your x coordinate. So as usual, the horizontal scaling sort of has a different, the opposite effect of what you would intuitively expect. Meaning, if your scale factor is between 0 and 1, your parent function, let's say it starts out x squared like that, your transformed function is going to be flattened out like that. And so we call that a horizontal stretching because the points are moved, are stretched over like that. Okay, so that's if your value of b is between 0 and 1. Now, if your value of b is greater than 1, then your graph is going to become skinnier, basically. So greater means skinnier. So do you see how that's counterintuitive? Greater makes it skinnier, and in between 0 and 1 makes it wider. Okay, so our points are then going inward when you have a b greater than 1. Now let's see why that occurs. Okay, so we're going to try to understand how this horizontal scaling affects our x-coordinate of our parent function. So once again, I've taken 2 points, 1, 1, and 2, 4, and I want to find out what happens to those 2 points. So let's do the purple one first, where the 2 is, and let's look back here. So that's this case here, where my number is bigger than 1, and we're going to expect that we're going to get a compression or a contraction, so it's going to become skinnier in the x direction. That's what we're expecting. So for the purple one then, we're going to figure out the new coordinate pair. So we're only affecting the x values of our original point lying on the graph of the parent function. So the y value isn't going to change here. So we're going to figure out the x value. So if our transformed function, let's call it g of x, is 2x squared, we use the inside part to set it equal to the old x coordinate. So for the point 1, 1, we're going to set 2x equal to the x coordinate of 1 and solve for x. X is going to be 1/2. So the point 1, 1 becomes 1/2 1. So it's moved inward by that amount. Scale, horizontal scaling. All right, so let's now do the point 2, 4. So the x coordinate is 2 equal to 2x on the inside. So if I divide by 2, I'm going to get x is equal to 1. So the point 2, 4 becomes the point 1, 4. So 1, 4. So I've got in this much. So I've shrunk. I've scaled. Now you wouldn't expect these two distances to be the same when you're multiplying. It's different than adding. So scaling doesn't cause the same distance shift in your x-coordinate. Okay, so it's a factor of 2 here, causing this to become contracted in the x direction. Okay, so now we're going to do the black function, 1/2 x squared. So going back here, we're talking about a scale factor between 0 and 1. So we expect it to expand outward. Remember, it's the opposite effect. So if you have a smaller number in front, it gets wider. If you have a bigger number in front, it gets skinnier. All right, so now we're going to look at the black function. So we're going to call that, let's call it h of x is equal to 1/2 x squared. Okay, remember the scale factor inside the parentheses changes your x value of your point that you're transforming. So I'm going to transform once again 1, 1 and 2, 4. So I would expect the y value to stay the same and the x value to change. All right, and it's the opposite effect. If I have a 1/2 in here, my graph is going to get wider. So the smaller number, wider, right? The bigger number, skinnier. Opposite effect when you're dealing with horizontal stuff, horizontal transformations. So I'm going to say that 1/2 x, the part on the inside, is equal to the x-coordinate and the point 1, 1, so that's 1. So if I multiply by 2, I'm going to get x is equal to 2. So my transformed point from 1, 1, I'm going to go to 2, 1. So that's this point here. So I've gone here. Okay, so now the x-coordinate of the point 2, 4 is 2. So I'm going to set that equal to 1/2 x. I'm going to multiply by 2 again. So I get x is equal to 4. So my point 2, 4, so that's 2, 4 up here, now becomes 4, 4, 4, 4. So I've expanded out to here. Expansion. Okay, so now, so that pretty much takes care of it. So you can see if your number inside is greater than 1, you're going to get skinnier, narrower. If your number out the front here is between 0 and 1, you're going to get wider, and this affects only the x value. Okay, so the last thing we're going to do is we're going to do a transformation problem that has multiple translations to the x and to the y, all occurring in one example. Okay, so let's break this down first. So if I have g of x is equal to all of that right here. I'm going to take this 2, I'm going to put it under the 4, and I'm going to put it under this other part here to break it up into 2 pieces. So I've got 4 over 2 minus 3 over 2 times f of 1 minus 2x. All right, so what's going on here is that this function here is our f of x, and we're going to take this function, this original f of x function, and we're going to perform these transformations on it and sketch the new graph. Okay, so what we've got here now is 2 minus 3 halves f of 1 minus 2x. Okay, so let's put it in the order that we like to see it in generally. 3 halves, negative 3 halves, f of 1 minus 2x, and then this would be an up 2. Okay, so this part on the inside is going to affect your x values. This part on the outside, these 2 parts on the outside, are going to affect your y values. All right, so let's write that up here on the top. So we've got negative 3 halves f of 1 minus 2x plus 2. Okay, so this is y, and this is x. The next thing we're going to do is we're going to list our points that we have. So we've got negative 4, negative 3, negative 2, 0, 0, 3, 2, 0, and 4, negative 3. Now we're going to figure out where those points go by applying our transformations, and then we're going to get a new point. So our x's and our y's are going to change because we have all these different transformations happening together. So let's do it systematically. Let's do our x's first. So I've got, for the first point, I've got an x value of negative 4, and we're going to set it equal to the inside 1 minus 2x and solve for x. So that's negative 5 is equal to negative 2x. X is equal to 5 halves. All right, so that's 5 halves. All right, let's keep going on the x's. So on the second one, we've got negative 2 is equal to the inside. So I've got negative 2x is equal to negative 3, so x is equal to 3 halves. All right, and then on the third one, I've got 0 is equal to 1 minus 2x. So that's negative 1 is equal to negative 2x, or x is equal to 1 half. And then I've got 2 is equal to 1 minus 2x. So I've got minus 2x is equal to 1. So x is equal to negative 1 half. And then lastly, I've got 4 is equal to 1 minus 2x. So negative 2x is equal to 3. X is equal to negative 3 halves. All right, so we've finished the x coordinates. Now let's do the y coordinates. So what we've got going on here, now let's see if we make sure we can understand this. So let's just highlight it in the original equation here. So you're multiplying here and you're adding here, okay, where this is your y coordinate here, your f of whatever. Okay, so we're gonna do that to each one of our y coordinates. So on the first one, I've got a negative 3. I'm going to multiply it by negative 3 halves and add 2. So that's 9 halves plus 4 halves. So that's 13 halves. All right. So we're going to keep going. Now remember, you can speed these videos up when you're playing them back to double time. It'll make this process go a little faster. So I'm going to take 0, and I'm going to multiply it by negative 3 halves, add 2, so that'll give me 2. Now I'm on 3. I'm going to take 3, I'm going to multiply it by negative 3 halves, and add 2, so that's negative 9 halves plus 4 halves. So that's negative 5 halves. Okay, now you want to do these calculations by hand. So you need to get really good at dealing with fractions when you're in pre-calc. All right, so I've got 0 again. So that's going to be the same as the one that had the 0. So that's 2. This 0 here, same. All right, and then I've got a negative 3 here, so I should get the same number, 13 halves here, so that speeds it up a little bit. All right. Now let's put those dots on our graph. So 5 halves, so that's 2.5. 13 halves is 6.5. So that's 2.5, 6.5, 2.5. So we got to make it a little bigger here. 4, 5, 6, 6.5. All right, so 2.5, 6.5. All right, and then I've got 3 halves, 2. So that's 1.52. And then I've got 1 half, negative 1 half, and negative 2.5. And then I've got negative 1/2, 2. And then I've got negative 1.5 and 6.5 again. All right, so now we're going to connect it. And that's our translated graph. This looks like a sine graph or a cosine graph. Okay, so we've done it point by point. All right, so you should be ready to tackle the homework problems now. And if you have any questions about this transformation information, just let me know. The main thing that you want to keep in mind is the inside part affects the x values of the coordinate pairs that you're transforming, and the outside parts affect the y values.